All right, our next presenters are Ryan and Sergio. They've been working very hard with the physics department this summer to explore entropy.
Hello, like she said, Ryan, I'm Sergio, and we're studying entropy. Just for a little background, this first picture is a good explanation of what entropy really is. On the left, you have this box with evenly divided blue and red dots, and you can easily decide where the blue and the red dots are in this box. But then you move this divider, and you get this evenly spread out distribution of dots everywhere, and it becomes a lot harder to predict where the dots are going to be or which dot you're going to pull out if you put your hand in there. So that's pretty much what entropy is. It's the level of disorder or unpredictability in a system, or in this case, the boxes.
Okay, thank you, Sergio. Next slide. Okay, so in our project, we've been working with complex systems. And a complex system is just basically a system with lots of interacting parts that play with each other and make weird signals. So, because they interact with each other in unknown ways, it can be really challenging to quantify the behavior. And it's a lot harder to predict when parts are going to pop up on graphs we get. Next slide. Okay. The most basic complex system that everybody can play with, I guess, is just a basic water faucet, which can be coherent, random, or chaotic. So when it's coherent, it drops like every second, and I can tell exactly when the next drop's going to hit. When it's random, you crank it just a little bit more, and it starts like being more erratic. And in between coherent and random, you get chaotic. And if you look at it for a little bit, it looks very, very random. But eventually, over time, it develops a pattern. Okay, our system that we used was this chaotic pendulum here, or a complex pendulum. So basically, there's a motor here, which can be seen right here, kind of. That spins and Oh, hey. Okay. So the motor's right here, and it's attached to strings, which are a little hard to see, which connect to this disc here. And the strings are attached to springs, which just make it oscillate a little differently. There's a magnet here, and I'll talk about that in the next slide. But we can change the oscillation by changing the hertz on the motor here. Next slide, yeah. Okay, we measure the angular position over time. So this angle right here is 0, and as the pendulum oscillates, it moves back and forth. And over here on the left side is negative, and over here on the right side is positive. And that's how we get our graph data. Okay, the parameters that we change are the magnets here. So there's one magnet here, which can be moved closer and farther from the disk, which has another magnet on it. So that allows the disk to either become more attracted to this magnet or repel, and that will make it oscillate differently. And this is Sergio's time to shine.
Okay. So the information we gather from our complex system is, as Ryan said, we have a graph, which is angular position versus time. Here's explain that. Also, we have entropy. And like I said at the beginning, entropy is a measure of the disorder in a system. And the different behaviors that systems can fall into have a specific level of entropy that they're associated with. So here's a graph of an angular position versus time. And this is with a weak magnetic field. Now, by studying this graph, we can make a guess of what kind of entropy we're going to get. As you can see, this graph goes up and down, very nice and periodically. But as you notice, the data points all line up very neatly, which means that the entry is going to be very low. It's like having the boxes split up into two sections. It shows that if I'm going to decide where a point's going to show up, I have a limited amount of options, which makes it easier for me to do that. Here is another angular angular position versus time, my bad. But in this case, it's a strong magnetic field, and as you can see, the points are more evenly distributed, and not only that, but the way the pendulum oscillates isn't as periodic. You can see peaks that come up once in a while, but even the peaks don't line up very neatly. So by looking at this, you can make a guess with entropy, knowing that it's the disorder of a system that, since the points are evenly distributed, it's harder to take a guess of where the next point's going to appear. So again, entropy. It's a measure of a system's disorder and predictability. It's kind of like deal or no deal. The less cases you have, the bigger chance you have of knowing what's in those cases. While the more cases you have, it's harder to tell what you're going to get when you pick a case. And this ties into how we look for entropy, which we'll talk about in the next slide. So as I mentioned, that deal or no deal example ties in with the first method of finding entropy, or the first step we take. This step is binning. And what binning is taking the graph and splitting it into increments, which help us look for points. So if you have a graph, you may break it up into increments of 0.1 radian of width. And in that 0.1 radian of a width, we'll look for points and see how many points appear over a long period of time in the graph, and that'd be considered a bin. After that, we find the probability of finding a point in the bin. So it's like saying how many points are in that bin and what's the chance of me finding a point, which is also known as the frequency. After we find the frequency, we take each frequency individually and plug it into this equation. And then we sum all the terms up together to get what we consider a number for entropy. This equation is Shannon's entropy equation, which was derived by Claude Shannon. And for the sake of time, we can't really explain how he got it, but mathematically, it's accepted and it fits with the data. Okay, so this is how we use both graphs to observe or study entropy. As you can see, you have, again, that graph I was talking about that's neatly, the points are neatly distributed. They're distributed in these lines. And down here, you can see the frequency where you have each bin. So there's a bin here, and there's bins, but all these bins that you don't see anything have no points in them, which means that you have 4 possible bins, and out of those bins, you have one that's protruding, and which tells you that that one bin has a greater chance of having a point. So with this type of information, you can make a well-placed guess of where the next point is going to appear. And this is what we consider low entropy due to the fact that it's very orderly and predictable. So like I said before, we find the probability, and then we take the points count for each bin and divide it by the total number of points, or the sum, to find that. And then we normalize it, which is just taking that number and making it easier to understand by putting it in a scale of 0 to 1, where 0 is low entropy and 1 is high entropy. So for example, for this graph, after normalized, and we've done all that math, you get an entropy of 0.160, which is closer to 0 than it is to 1, which tells you that it's a low entropy. And like we described before, it is because you can see the points are in a low number of bins. So to show you what a system with high entropy looks like, again, we have this chaotic graph, not chaotic graph, but high entropy graph. And as you can see, when we did the frequency and we found the point count, you can see it's more evenly distributed than the other one is. You have a lot more chances of finding a point in different bins, which makes it a lot harder for me to tell you what's going to happen next. And the entropy is 0.643, which again is closer to 1 than it is to 0, which is apparent in this graph. So in order to study, we ran several tests, and we found that when we graphed the entropy versus the distance between the magnets as we were moving the magnet closer, that once you hit 1.5, you reach this point where the entropy suddenly spikes up rapidly. And so for our research, we wanted to find out what's going on in this region that's causing this to go from this nice, steady state to like, whoop, well, let's just go up there. So that's what we studied, and what we got was this. As we approached that area, we found that nothing didn't happen until we got to 1.5 centimeters apart between the magnets. Then we got this. This is a graph, obviously, but as you can see, you have this really kind of sporadic behavior with an entropy of 0.643, which we broke up to find out each section's entropy, which is pretty high. And then all of a sudden, it dies down into this nice, somewhat periodic graph. Now, the thing about this, though, is that even though it looks periodic, it's deeper due to the fact that you can see that the points don't all line up, which means they're not coming at a periodic rate. But the entropy is 0.43. That's because, like I said, they're not coming. The points aren't all lined up, which gives you higher entropy. And the total entropy is 0.558, which we found was pretty interesting. So we consider this as just a sudden transition to a more ordered state, which makes some sense with that number. So for conclusion, we wanted to ask, what does entropy really tell us in a system? And what we found out was it tells you the predictability of a system, and like I said, the disorder of a system. It can help tell you what you can expect out of the system, and it helps tell you how much information the system is going to relay back to you. For future study, we want to study that transition point, like why does that happen, and how does that happen, and why does it happen the way it does happen. And also double pendulums, which are just two pendulums on one, which is just another degree of freedom, or another way that pendulum can express its energy, which just makes the system more complicated. And finally, I'd like to thank XL Energy and Kinder Morgan for their support. Also, the physics department with Dr. C-Mac, Kai Fick, Tim O'Neill, Steve Champion, and obviously the office with Lori Ball, Karen Allnut, Yvette Casadena, and Chris Krause. Sorry.
And also our individual sponsors, which could not have been fit up there due to the size. But we'd like to give a shout out to them. Kevin and Mona Lear for me, and
Bacon Foundation, thank you.